Hi, my name is Dan, and this video is one in quite a large series of videos which chart in the progress of creating a 4-bit, a simulated 4-bit CPU out of basic logic gates. And a roadmap of where we're up to and where we're going is down in the description below, as is a link to the free digital electronics simulation software that we're using called DigitalWorks. And where we're up to is we're quite late on in this process now, and this subset of videos is going to be looking at the control unit. And we're going to start by thinking about what the control unit does and doing a little bit of planning, and then for the rest of this series, short series within the larger series, we're going to actually be creating the control unit. If you don't know what a control unit is, then you're probably not going to understand this video. This whole set of stuff is kind of like a pyramid, so you need to know previous things to be able to understand stuff as we are here, and we're quite a way down the line. So if you wanted to know all about this, then check out the other videos, the previous videos on this. This uses digital electronics, and so you need to understand what gates are and what they do, and a whole lot of other stuff as well. And by this stage, we've actually got quite specific. Early on in the process, we were fairly generic, and we were making things like registers and decoders and multiplexers that are quite versatile components used in many different settings. But we're now very much tied into a specific CPU design. And if you want to know what that CPU design is, then the previous short set of videos to this one have charted that. And so this should be by no means taken as how to design any control unit for any CPU. It is very much how we're doing this control unit for this CPU. And control units vary quite a lot in terms of how they work and the complexity. We've taken a fairly simplistic and ham-fisted approach, and that's going to follow through into the CU, the control unit, in order to make it relatively accessible, easy to make, and fairly easy to understand, I hope. Out of all the components in the CPU, the control unit is possibly the hardest to get your head around. So if you do, then congratulations, that's great. Let's think about what it does then. So the control unit is this magical box that makes everything happen inside your CPU. Obviously, it's not really magical. It tells everything else what to do. So what it does is it looks at the opcode, which is the code that the programmer uses to tell the computer what to do, and it actually works out what the hardware needs to do to affect that opcode. So the tasks that the control unit needs to do, let's break those down. Well, in our control unit, we're also going to deal with the fetch cycle, or the fetch part of the fetch execute cycle. So we're going to receive the phase signals from the ring sequencer. Again, if you don't know what that is, look at the fetch execute video that I did for the CPU design. And there'll be two signals from there. There's the fetch 1 and the fetch 2, because we're doing it in two parts. So it turns those into appropriate commands, and I'll explain what I mean by commands in a minute. It also takes the execution signals, and again there are two of those, x1 and x2, into the appropriate commands depending on the opcode, which has been stored in the op register, which has been got there by the fetch 1 and the fetch 2 commands. So effectively the command unit has grabbed its own opcode in order to work out what it needs to do. So commands, what do I mean by this? Well, they're not codes or binary numbers. In fact, each potential command effectively is a wire, not a physical wire because we're using a simulator, And when that wire goes high, it makes something happen. And there are several of these floating around. We've made some of these components already that we can plug in, so you should understand some of these. Output enable to a register uh, to tell it that it is going to be the thing that tells the bus what the values are being held in the bus. Bus read to a register. So between those two, when one register has output enable and another register has bus read, that effectively copies the data from the first register to the second register. Memory read or write to a memory bank, and if you've been through the stuff with the memory bank that we created, you'll hopefully remember that as well as putting the information into the data register and the address register, you also need to do a read or a write to actually get that into the memory bank or out of the memory bank. Execute to the ALU. The ALU has a range of commands that it can deal with, but it needs to know that it's actually going to have to actually do something. And the ALU, we've built it already, has an execute pin on it. And there are some others. In fact, let's break this down a bit more and think about the actual these commands and the opcodes, and we'll do fetch execute as well. So halt is our most basic opcode to tell everything to stop, and basically our ALU is going to have a halt output, and we'll work out what to do with it a bit later on. The Some of our opcodes are data transfer. We're calling those our reg commands because they're using registers, and so this is fairly obviously output enabled to one reg and bus read to another reg. Some of these also need a memory read or write to make them work if you're accessing things that are inside one of the memory banks. We've also got jump commands. So 2 out of the 3 of those have conditions. So we want to check the conditions, and then uh, uh, if the jump is happening, it's actually just another reg command. Effectively, is that you're transferring data into the program counter. There's another little wrinkle on that, is that if you do a jump, you don't want to increment the counter, um, the program counter at the end of the cycle. But we'll come back to that. We will deal with that. And then ALU commands, we need to send the opcode and execute to the ALU. Actually, what we are going to do is we're going to hardwire the opcode from the op register into the ALU, but it will only actually act on that opcode if it gets the execute command. And then fetch one and fetch two. So fetch one is a data transfer and a memory read. So we need to transfer the memory address from the program counter, and then it does memory read. And then the second phase is also 2 data transfers where we get the op from its appropriate memory bank and the data from its memory bank and put them in op and data registers. Yeah, appropriately. Okay, so this means we've got lots of output wires from the control unit, and I guess this is what we might expect when we say that the control unit needs to control everything and control what's going on. When we set up the control unit, we'll start by setting up a whole lot of output stuff. Um, uh, let's break down the. Well, we've kind of already done this. Let's kind of aggregate some of these things into kind of broader categories, but it's breaking down the overall task of the control unit into subsets. So first of all, we need to deal with the fetch. We've talked about that already. We're going to we've got the question: what type of opcode do we have? Is it halt? Is it jump? Is it a register transfer, or is it an ALU command? And so we've got our 4 broad categories. We need to, if we've got a register command, we need to decode that and turn that into the actual individual commands that we need. Similarly, for the jump commands, we need to decode that. If we've got an ALU operation, then the ALU does the decoding for that. That's already built into the ALU, so we don't need to worry about that bit. So the things we actually need to do, in order to deal with the fetch, that's wiring. We don't need any extra gates in there just yet. We might need them in a little bit. What type of opcode do we have? We're going to make a macro to do that. I'm going to call it the op decoder. We're going to make a macro to decode the reg. We're going to make a macro to decode the jump. We don't need a macro for the ALU because the ALU does that already. So that's kind of a map of where we're going in creating this control unit. So in the next video, we're actually going to set up the basic output stuff and wires and things for the control unit, and we'll deal with the fetch commands in that video. But that's it from me for now.